If you were to somehow, like, strip the sun away right now, just remove it from the equation entirely, the Earth wouldn't just go dark.
No, not at all.
I mean, in a matter of weeks, it would become this totally frozen, lifeless rock floating in the absolute void of space.
Just a completely dead chunk of ice.
Yeah, but you step outside on a clear day, you feel that warmth on your face, you maybe squint a little bit, and then you just go about your business. We treat that giant blinding orb in the sky like a totally mundane appliance, like a porch light that someone thoughtfully left on for us.
It really is the ultimate background noise of our existence. I
Right.
mean, it's so omnipresent, so flawlessly reliable day after day that we don't even really see it anymore.
Right.
We just accept it, completely ignoring the reality of what is actually hovering over our heads.
Okay, let's unpack this. Because our mission in this deep dive is to completely reframe how you look at that giant bright thing in the sky. We are going to decode its hidden mechanics, its ancient energy, and the very real threats it poses to our modern world.
Because we really do vastly underestimate our relationship with the sun.
Oh, totally.
It isn't just the brightest thing you'll ever see. It is the source of very nearly all the energy that has ever mattered to life on Earth. Everything else is basically just a footnote.
Yeah, and you really don't need any kind of science background today, by the way. We're just two curious minds figuring out this incredible engine of our existence.
Exactly. And the sheer scale of our reliance on it is absolute. I mean, let's trace back a totally normal day. The food you ate today, that was built by plants using sunlight.
Right.
The wind that you might feel against your skin, or, the wind turning a massive turbine to generate electricity.
Yeah, wind power.
That is literally just air moving because the sun heats the Earth's atmosphere unevenly.
That makes sense for solar or wind power, but I mean, it goes so much deeper than that, right?
Oh, absolutely.
Like the petrol you put in a car is ancient sunlight. It was captured by plankton and plants millions of years ago.
Yeah, photosynthesis from millions of years in the past.
Exactly. Those organisms died, they sank to the ocean floor, and were compressed by time and pressure into oil. So even the coal we dig out of the ground is essentially just, well, stored starlight.
I love that. Stored starlight is a beautiful way to phrase it, and it's physically accurate.
Right.
When you burn coal, you are chemically releasing energy that a prehistoric plant absorbed from the sun deep in the Earth's past.
It makes me think about our daily energy consumption, like living off a cosmic trust fund.
In the cosmic trust fund.
Every time we drive a car or turn on a light switch powered by coal or gas, we are just spending this ancient solar inheritance, Like it was deposited into the Earth's bank account hundreds of millions of years ago. We're just trust fund kids blowing through our stored starlight.
We really are. We're cashing checks written by the sun eons ago without even a second thought. But here is the supreme irony of the sun's status as this almighty engine of everything.
Okay, what's that?
For all of its overwhelming importance to our survival, the sun is completely, wonderfully ordinary.
The ultimate average Joe of the universe.
Literally. It is a completely middle-aged average star. Just a vast ball made mostly of hydrogen and helium gas.
Wow.
There are hundreds of billions of stars just like it in our galaxy alone.
We should probably clarify the scale here, though, because, average in space terms is still pretty hard to wrap your head around.
Oh, for sure.
Like, the sun is so staggeringly large that you could fit over 1.3 million Earths inside of it.
Yeah, so it is massive to us. But in the grand cosmic lineup, it's remarkably unremarkable.
Right.
It only looks so incredibly unique and dominant to us because of real estate. It's close.
Location, location, location.
Exactly.
Yeah.
It's a mere 150 million kilometers away.
Which, to be fair, sounds like an enormous distance until you realize the next nearest star is Proxima Centauri, which is about 40 trillion kilometers away.
Right. So our entire existence, all of human history, every triumph and tragedy, depends entirely on this thoroughly unremarkable star that just happens to be in our neighborhood.
Which brings up a massive historical mystery. If the sun is just a giant ball of gas, how on earth has it stayed lit for so long?
That was a huge puzzle.
Because if it's just sitting there burning away, why hasn't it run out of fuel? In the 19th century, scientists actually tried to calculate this, right?
They did, yeah. Lord Kelvin, who was a brilliant physicist, he calculated that if the sun were essentially a giant bonfire.
Like a literal fire.
Yeah, even one made of pure coal and oxygen, which was the most efficient chemical fire they could imagine at the time.
Okay.
He figured it would completely burn out in about 30,000 years.
And 30,000 years obviously doesn't give you billions of years of planetary history.
Not even close.
So chemical burning was out. The answer wasn't actually worked out until the 20th century, and that answer is nuclear fusion.
Yes. What's fascinating here is that fusion is a fundamentally different way of releasing energy.
How so?
Well, we aren't talking about burning something. Fusion is about slamming things together.
Okay, let's break down the mechanics of that, because this is like the magic trick of the universe.
It really is. So deep inside the sun's core, you have gravity crushing the hydrogen gas with unimaginable force,
Just squeezing everything.
squeezing it so hard. We're talking about pressure that is roughly 250 billion times greater than the atmospheric pressure here on Earth.
250 billion.
Yeah. And this crushes and heats the hydrogen to around 15 million degrees Celsius.
But under those extreme conditions, you have a physical problem, right? The nuclei of hydrogen atoms, their centers, they have positive electrical charges.
And just like trying to push the two positive ends of a magnet together, they fiercely repel each other.
Right, they just slide apart.
They actively resist touching.
Mm.
But the gravity and heat in the sun's core are so intense, it overwhelms that magnetic resistance. It just forces them together anyway.
Wow.
They are slammed together so hard that they stick, they fuse. So step by step, 4 separate hydrogen nuclei are forced to merge into one single helium nucleus.
And this is the crucial moment, isn't it?
It is, because when those 4 hydrogen nuclei merge, the brand new helium nucleus that is created actually weighs very slightly less than the 4 hydrogen parts that went in.
Wait, really?
Yeah, there is a tiny sliver of missing mass.
Okay, I need some clarification on this missing mass concept, because in my head, it's like I'm trying to bake a 4-pound cake, and I put 5 pounds of ingredients into the mixing bowl.
Right.
Where does that extra pound physically go? I mean, you can't just lose matter. It has to go somewhere, right?
That is the perfect way to look at it. And
Yep.
you're right, the matter hasn't vanished into nothingness. It has been transformed.
Transformed.
That tiny sliver of missing mass has been converted directly into pure energy. This is the exact mechanism described by Albert Einstein's famous equation, E equals mc squared.
Ah, energy equals mass times the speed of light squared.
Exactly.
Most people know the equation, but the math behind why it produces so much power is totally mind-bending.
Let's look at the c squared part. The c stands for the speed of light, which is roughly 300 million meters per second.
Okay, which is already a huge number.
Right, and when you square that number, so you multiply 300 million by 300 million, you get 90 quadrillion.
Oh, wow. 90 quadrillion.
Yes. So you take that tiny microscopic sliver of missing physical mass and you multiply it by 90 quadrillion.
That is just wild.
The equation tells us that multiplying even a speck of physical matter by a number that large yields an absolutely apocalyptic amount of energy.
So when the sun fuses hydrogen into helium, that lost sliver of mass becomes the brilliant sunlight and the intense warmth that eventually crosses space to keep us alive.
Precisely.
And the scale at which this is happening is terrifying. I mean, the sun is fusing around 600 million tons of hydrogen every single second.
Every single second.
600 million tons
Yeah.
every time you blink.
And yet the sun is so unimaginably vast that it still has enough hydrogen fuel left in its core to keep doing this for another 5 billion years.
Okay, but wait, if you have 600 million tons of material essentially detonating with nuclear energy every single second, pushing outwards,
Right.
and immense gravity pulling everything inward, how does that not result in the star just ripping itself apart or like collapsing entirely? That balance can't just be a coincidence?
No, it isn't a coincidence at all. It is a permanent, beautiful balancing act called hydrostatic equilibrium.
Hydrostatic equilibrium.
Yes. The sun's stability is basically the ultimate cosmic tug of war. Gravity is forever trying to crush the star inward, pulling everything down to the center.
Okay.
And outward pressure from the nuclear fusion in the core is pushing back out against that gravity.
And they are perfectly matched.
Almost perfectly.
Yeah.
And the brilliant part is the mechanism that keeps the match. It is totally self-correcting.
How does it correct itself?
Well, let's say the core started to fuse hydrogen just a little bit faster than normal. The core creates extra energy, which creates more outward pressure, which puffs the sun up slightly.
So it physically expands.
It expands. But think
Yeah.
about what happens when gas expands, it cools down.
Oh, like an aerosol can getting cold when you spray it.
Perfect example. So the pressure inside the core drops, the temperature drops just a fraction, And that cooler environment naturally slows the nuclear fusion process back down.
Oh, wow. And it works in reverse, too, I bet. Like, if the fusion slows down, the outward pressure drops, gravity wins for a second and compresses the star.
Exactly.
And that compression heats the core back up, and the fusion speeds up again.
It functions exactly like a thermostat in your house. It is a self-regulating engine. It is not a bomb exploding in space, you know. It is a contained, continuous, perfectly balanced machine.
That's incredible.
And that equilibrium is the only reason the sun has shone steadily enough, for long enough, for life to evolve on Earth.
Here's where it gets really interesting, though, because that elegance makes sense on a macro scale, but thinking about the light itself radiating out from that core, getting out of the sun is actually incredibly difficult for that energy.
Well, it is a profound struggle. You intuitively think the light is created in the core and just shoots out into space at the speed of light.
Yeah, like turning on a flashlight.
Right. But the interior of the sun is unimaginably dense. It is a thick, crowded soup of atomic nuclei and electrons.
So a packet of energy, a photon created in the core, can't just fly straight out.
Not even close. It travels a fraction of a millimeter before it slams into another particle, gets absorbed, and is then re-emitted in a completely random direction.
Just pinging around.
Physicists call this the random walk.
It's like the world's most frustrating, impossibly dense pinball machine, just packed with billions and billions of bumpers, and the pinball is just bouncing off every single one, staggering around like someone lost in a massive crowd.
That's exactly what it's like.
So how long does it take for one single ball to finally reach the surface?
Because of that random walk, taking microscopic steps back and forth, up and down, it takes tens of thousands of years.
No way.
Possibly even over 100,000 years, for that energy to zigzag its way from the core where it was made up to the surface of the star.
That is wild. So the sunlight warming your face right now, like the light itself left the sun's surface just 8 minutes ago.
Right.
But the actual energy inside that light, that was generated in the core of the sun back when human beings were living in the last ice age.
Ice Age energy, slowly fighting its way out for over 100 millennia, just to hit your face on a Tuesday afternoon.
But once that ancient energy finally does break free from the dense interior, things get really chaotic.
Yes, they do.
Because it reaches the surface, which is called the photosphere. And this is where I need to challenge the physics again, because the temperature gradient here makes absolutely no sense to me.
It is very counterintuitive.
Yeah, because the photosphere, the part we actually see, sits at around 500 and 500 degrees Celsius.
Which is relatively cool compared to the 15 million degree core, but still fierce enough to glow brilliant white.
Right. But above that surface, you have the sun's outer atmosphere called the corona. And the corona is far hotter than the surface below it. It is millions of degrees. Hold on, that's like standing right next to a roaring campfire and feeling a little warm, but then stepping 20 feet away from the campfire and suddenly getting incinerated. How does that make any physical sense?
It's crazy, right? It is one of the great open questions in solar physics. It's known as the coronal heating problem.
So we don't even know for sure.
Not entirely. You naturally expect things to cool down as you move away from the heat source. Why the corona spikes to millions of degrees is a massive mystery. In fact, humanity is currently flying space missions, like the Parker Solar Probe, closer to the sun than ever before, specifically to figure out this exact puzzle.
Wow. One of the leading theories involves the magnetic fields, right?
Yes, exactly.
Because the sun doesn't just sit there glowing. It is a highly active, violent environment. It blows off this constant stream of charged particles called the solar wind, which flows out past all the planets.
Yeah.
And it has extremely violent space weather.
Yeah, the sun is essentially a giant ball of electrically charged plasma. And as it rotates, it generates colossal magnetic fields. But because the equator of the sun rotates faster than its poles, those magnetic fields get incredibly tangled and knotted up.
How does a tangled magnetic field create weather, though? Like, what does that actually look like?
Well, think of the magnetic field lines like incredibly thick, powerful rubber bands being twisted tighter and tighter.
Okay, building up tension.
Exactly. Eventually, the tension becomes too much. The magnetic bands snap and realign. And when they snap, they release a staggering amount of stored energy.
Oh, and that snapping is what causes solar flares.
Exactly. And the larger snaps result in something called coronal mass ejections, or CMEs.
A coronal mass ejection, it sounds like something out of a sci-fi disaster movie.
Yeah, it really does. A CME is a massive eruption that literally flings billions of tons of physical matter, electrically charged plasma out into deep space at millions of miles per hour.
And sometimes the Earth happens to be right in the firing line of that blast.
Unfortunately, yes.
And when those charged particles hit us, some beautiful things happen, but also some incredibly dangerous things.
The beautiful consequence is the auroras, right?
Right.
The northern and southern lights.
Right. The Earth has its own magnetic field, so when the blast of solar particles hits us, our magnetic field largely deflects it, funneling those charged particles down toward the north and south poles.
Oh, so that's why you see them at the poles.
Yes. When they hit our upper atmosphere, they excite the gases, creating those glowing, dancing lights. And we should be very clear here, the Earth's magnetic field and our physical atmosphere provide an incredible shield.
So they're safe.
These solar storms are absolutely no direct physical danger to your biological body. You are safe on the ground.
Okay, so our biology is perfectly shielded, but the technological nervous system we've built around the globe, that is entirely exposed.
Completely exposed.
So essentially, humanity has built an incredibly fragile, high-tech glass house right next door to a totally unpredictable neighbor who occasionally throws rocks. That's the perfect analogy. And if we connect this to the bigger picture, this is where the sun goes from being a benevolent provider to a very real hazard. Because while biology is shielded, electricity is not.
Right.
A powerful solar storm can induce massive electrical surges in our power grids.
We're talking about geomagnetically induced currents. These invisible waves of magnetic energy sweep over the Earth and literally push electricity through any long metal wires they find on the ground.
Yes, and they overload high-voltage transformers, potentially melting them from the inside out and causing widespread, long-lasting blackouts.
Which is terrifying.
It is. Furthermore, they can completely disrupt the satellites we rely on for global communication, for navigation, and for predicting our own earthly weather. They can knock out radio transmissions and take down GPS systems globally.
And we know this can happen because it already has.
It has, yeah.
In 1859, there was a huge solar storm known as the Carrington event, named after Richard Carrington, the astronomer who actually saw the massive flare erupt on the sun through his telescope.
The 1859 storm was so immense that auroras were seen as far south as the Caribbean and Hawaii.
That's crazy.
The sky was glowing so brightly at midnight that people woke up and started making breakfast thinking the sun was rising.
But the real impact was on the technology of the time, right? The most advanced infrastructure in 1859 was the telegraph system.
And this solar storm was so intense that it set telegraph systems literally sparking.
Like physically shooting sparks.
Yes, operators were getting physically shocked by their equipment. In some offices, the telegraph peeper caught fire.
Oh, wow.
Operators even found they could unplug their batteries and still transmit messages from city to city, powered entirely by the electrical current the solar storm was inducing in the wires.
That is just wow. Now, apply that to today. Our world is infinitely more electrified than it was in 1859. We are completely dependent on delicate orbital electronics, global supply chains managed by GPS, and an aging electrical grid.
It's a huge vulnerability.
If a Carrington-level event hit us now, the disruption could be catastrophically expensive and devastating to modern life.
Which is exactly why we now have space weather forecasters.
Oh, really?
Yeah, there are agencies constantly watching the sun with dedicated satellites, exactly the same way meteorologists watch the oceans for hurricanes forming.
That makes total sense.
Because the more wired we become, the more orbital our civilization gets, the more it matters when our benign, life-giving star loses its temper. We have to keep a very close eye on it.
So what does this all mean? We started out by saying we treat the sun like a mundane appliance, a porch light we take for granted. But after looking at its true mechanics, that is impossible to do.
It really is. When you hold the full reality of the sun in your mind, it's profoundly awe-inspiring.
Yeah.
It's an entirely ordinary star, just one of hundreds of billions. But every single second, it crushes 600 million tons of hydrogen into helium. It turns a tiny whisper of missing mass into pure energy, multiplied by the speed of light squared.
Energy that staggers through an impossibly dense core in a random walk for 100 millennia, finally breaks out of the surface, crosses the absolute emptiness of space in just 8 minutes, and arrives here.
Arrives here to do literally everything.
Arrives to grow the food you eat, to drive the ocean currents, to create the wind, to warm the air you breathe.
And it maintains this blistering output in perfect stability because the incredible crushing force of gravity and the explosive outward pressure of nuclear fusion have fought each other to a flawless, self-correcting draw.
A perfect draw that will hold for billions of years more until eventually, in the distant future, that fuel will run low, the balance will fail, the star will swell into a red giant, and it will end the story of our solar system.
This raises an important question, I think. Something for you to ponder long after we sign off today.
I love a good takeaway.
We established earlier that every gust of wind, every single bite of food you take, every piece of coal or drop of petrol we burn is literally just stored solar energy.
Right, it's all tracing back to that core.
So if our entire physical existence is fueled by this process, if the energy currently moving your muscles to breathe or powering the neurons in your brain to comprehend these words is just transformed sunlight, aren't we just the sun's energy experiencing itself?
Oh, man.
We always look up and think of the sun as this separate object way up there in the sky. But physically, down to the atomic level, its ancient energy is what is animating our very bodies down here.
We are walking, talking, stored starlight. I absolutely love that. And on that note, we want to warmly thank you for joining us on this deep dive today. We hope you never step outside, feel that warmth on your face, and look that ordinary, extraordinary star the exact same way again.